Chapter 2.2, Subsets. So we've already talked about what a set is. It is a collection of objects where we will refer to those objects as elements or members of the set. Now a subset is essentially a set within a set. If set A is a subset of B, then that means that all the elements of set A are also elements of set B. The symbol we use looks like a rounded less than or equal to sign. It's read as set A is a subset of set B when we write A, that symbol, B. So we can think of it very much like the way we think of a less than or equal to sign. It shows that set A has all or less of the elements of set B. It has all would be their equal or less, meaning it is sub to that larger set. In the same way that less than or equal to means we are either less or we're equal. We can also say the subset symbol with a line through it means it is not a subset. So A is not a subset of B means we would write that symbol with the line through it, in the same way that we would say something is not less than. To show that set A is not a subset of set B, we just need to find at least one element of A that is not an element of B. So if we have A is boat, train, plane, B is train, boat, car, plane, and C is boat, bike, car, plane, train, we want to sort of show which of these sets is a subset of the other. First, I'm going to draw out each of the elements, right? So I'm going to sort of introduce the idea of a diagram to us. We're going to get a lot more into these in the next chapter, but for right now, we're just going to think about, I'm going to put a circle around any elements that are in A, right? So that's train, boat, and plane, right? So that's all of this, like so. So that is what's contained in A. Then B is train, boat, car, plane. So it's got this three things that are in A, but then we add in the car to make B. And finally, C is boat, bike, car, plane, train. So it has the four elements that were in B plus one more, bike. So we can say, visually, A is within B, which is within C. So A is a subset of B, A is a subset of C, and B is a subset of C. But we wouldn't say C is a subset of A, or C a subset of B, or B a subset of A. None of that is true. It matters which direction we're going. Because in essence, we would say A is less than B. That's what the subset thing means. It has less elements, but still the same elements, just less of them. And B has the same elements of C, just less of them, or equal. Now, if we get rid of that or equal, we get what is called a proper subset. So a proper subset, symbolized using the same sort of symbol as the subset symbol, right? It's this rounded symbol that looks like less than or equal to sign, but now we got rid of the or equal to part of it. Means that sets A and B are not equal, but set A has less than B. It has less of the elements, but the same elements. So set B must contain something that is not in set A, but set A does still have only things that are in set B. So this is read as set A is a proper subset of set B. Again, you can think of it as just like a less than sign, showing that set A has only elements that are in set B, but explicitly less of them. So here, you have four sets of letter elements, and we want to know which ones are subsets, which ones are proper subsets of each other. So let's look at this. So is C a subset of A? Well, C has the elements A, B, C, D, and A has the elements A, B, C, D. So everything that is in C is also in A. So yes, it's a subset. It happens to also be equal, but C is not proper because of that equality. So this is yes, this is no. Then is B a subset of A? So we look A, B, C. All of those elements are in A, so B is a subset of A. And in fact, A has an extra element that B doesn't, so B is a proper subset of A. Is D a subset of A? Well, D has A and E, and, well, A has little a, but it doesn't have E. It has this extra element, so no, it's not a subset, and if it's not a subset, it definitely isn't a proper subset. Is B a subset of itself? Now, that's an interesting question. B is itself, right? So B is equal to B. So B has all the elements B has. So yes, B is a subset of itself. But it can never be a proper subset because, of course, B doesn't have less things than it already has, right? That would be some sort of weird paradox. And finally, is the empty set a proper subset of A? In fact, it is. If I take A and I want to pull some things out of A, then that's how I get subsets. And if I just happen to pull nothing out, I haven't broken my subset definition rule here. So yes, in fact, the empty set is both a subset and a proper subset of A. The empty set is a subset and a proper subset of all of them, in fact, because I can always choose to take nothing. So think about subsets as being, we take the main set, so in this case, A, for 4 out of 5 of these questions, we take the main set, and I'm just pulling elements from it. And if I pull all of the elements out, then I have a subset. If I leave some behind, then I have a proper subset. And if I just choose not to take any, it's still a proper subset. I've been pulling things out, I just didn't. And then I left stuff behind, so it's proper. Now what about how many different combinations of subsets can I have for a given set? So if there are n elements in set A, so the cardinality of A is n, then we can create 2 to the n different subsets of A. And since exactly one of those will be perfectly equal to A, remember when I say different subsets, I mean order does not matter here. 1, 2, 3, and 3, 2, 1 are the same thing, so we're not counting that twice. So there's only one time that our set will be equal. Then we can say that the number of proper subsets is 2 to the n of minus 1, because we remove that one main set. So let's look at the elements in the word sled. We're going to create all of the proper subsets, and we know what the final non-proper subset is. It is A itself, right there. So n of A, or the cardinality of A, remember this is cardinality means how many elements are in it, is 4. Because there are 1, 2, 3, 4 elements. Then we plug into our equation for proper subsets 2 to the 4th minus 1. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. Minus 1 gets us 15. So there should be 15 proper subsets. So let's list them. Now, notice that I've written the number of elements for each of these subsets. And see that I have one that lists 0 elements. Because, as we said on the previous slide, the empty set is always a proper subset of, the empty set is always a subset of any set we have. So we can't forget that one. So we start with the empty set. That's the easy one, right? I can use either the empty set symbol or just the empty curly braces, either way. Then the one element sets are going to just be the sets containing S, L, E, and D. The 2 element sets are going to be SL, SE, SD, LE, LD, ED. Then the 3 element sets, SLE, SLD, SED, LED, all of these, right? So these are all the possible sets, and if we count them, I get, there's 1, 4, 6, 4, so that is 10, 15. There's 15 of them, just like we would expect. So knowing this formula It's going to be very helpful to help guide you if you're missing any. And one you're probably most likely missing is that 0-element set, because that one gets skipped quite often. But just be careful when you're listing them out. You do need to know this formula for the record, so make sure you know the formulas and know the difference between when we're talking about the proper ones versus just in general. If I ask for the number of subsets, it's 2 to the n. If I ask for the number of proper ones, we remove 1 to get 2 to the n minus 1. Because that final proper set, that final non-proper set is the SLED. It's the one containing everything.